Hello friends, how are you? I hope you all are good and doing well. In the present video lecture, we will be talking about the measurements in the quantum mechanics and expectation values. We'll talk about how measurements disturb the quantum system and what is the expectation values and how can we calculate the expectation values. So let's start the video lecture. Friends, myself Virendra Kumar, professor and scientist, and you are watching the Sai Academy channel. Friends, in classical physics, it is possible to perform measurements on a system without disturbing the system. In quantum mechanics, however, the measurement process disturbs the system, perturb it while measuring the observables. While carrying out the measurements on classical system, this perturbation, this disturbance also happen, but because of the microscopic scale, this disturbance, this perturbation is very negligible. But in quantum mechanics, we talk about the atomic scale, subatomic scale system. Therefore, the act of measurement in the quantum system induces the disturbance which can be negligible. To make it more clear, let us take an illustration by considering an experiment that measures the position of a hydrogenic electron. For this measurement, we will have to bombard the electron with electromagnetic radiation, that is photons. So if this is hydrogenic electron and we want to measure the position of this electron, we need to bombard EM radiation. We need to torch some light on this. Light means here EM radiation to observe the position of this electron. If you want to determine the position of this electron very accurately, then the wavelength of the radiation must be sufficiently short. How much short? Since the electronic orbit is of the order of 10 to the power minus 10 meter, then that then the incident radiation should have the wavelength less than this dimension. That means the wavelength of the radiation should be less than this order. And for that you must use a radiation which is smaller than the 10 to the power minus 10 meter. And let us calculate how much energy in that case the radiation will have. We can calculate the energy of the incident radiation in that case by formula h nu is equal to hc by lambda, and substituting the values for this, 3 into 10 to the power 8 meter per second divided by 10 to the power minus 10 meter. So order for this energy would be equivalent to 10 to the power 4 electron volt. And we know that this much energy will be so intense that will strike the electron and it will knock it out from the orbit of, because you know that the ionization energy of the hydrogen atom is about the order of 13.5 electron volt, which is very less in comparison to this. That means this much energy will be so intense that the electron will leave the orbit. Thus, the mere act of measuring the position of the electrons accurately will disturb the electron appreciably. Friends, I think you grasp this concept how the measurement of the electron's position will be going to disturb it significantly while we want to measure this electron's position very accurately. Let us now talk about the general concept of measurement in quantum mechanics. The act of measurement generally changes the state of the system. For measuring an observable in quantum mechanics or in theory, we use an operator as a device. Let us consider a system which is in state ket psi. Before measuring an observable A, the state psi can be represented by a linear superposition of the eigenstate ket psi n of this operator A. So we can write the system state ket psi in terms of the superposition of the eigenstate ket psi n of the corresponding operator given by summation n ket psi n bra psi n. As per the basic postulates of quantum mechanics, the measurement of an observable A may be represented by the action of the operator A on the state vector ket psi, and the possible result of such a measurement is given by one of the eigenvalues an of the operator corresponding to the eigenstate psi n of the operator. If the result of the measurement of A on the state ket psi is an, then the system immediately after the measurement is given by a projection of psi onto the eigenvector psi n corresponding to the eigenvalues an as psi after measurement is equal to ket psi n bra psi n ket psi, which can be written as an ket psi n. Now suppose the system is already in the one of the eigenstate of the operator A, then in that case the measurement of the observable certainly yields the eigenvalues an without changing the state psi n. I think you understand this. Suppose here I am talking about the suppose here the system is already in one of the eigenstate of the operator. In that case, we want to measure the observable A over this state psi n, then the eigenvalue will be an and the resultant state vector will be in the psi n ket psi n also. There will not be change in the state because system is already in the eigen state of the operator A. This is an exception in this particular case. Before a measurement, we don't know in advance with certainty in which eigenstate among the various state ket psi n a system will be after the measurement. That means we can't say by guarantee that after measurement in which state the system will be. Only a probabilistic outcome is possible, and that is given by the basic postulates of quantum mechanics, that is the probability of finding the system in one particular non-degenerate eigenstate psi, and that is given by Pn is equal to modulus square of bra psi and ket psi divided by the bra psi ket psi. If the system is already in normalized state, then this denominator will be equal to 1, else we will have to find the normalization constant for the system. It is the effect of the interference by the equipment on the system which is the essence of quantum mechanics, and for that certain measurements cannot be performed without major disturbances to other properties of the quantum system. We will find the expectation value of an operator with respect to a state psi, and that is defined by expectation value of an operator is equal to bra psi operator A ket psi divided by bra psi ket psi. For example, let us take that we want to measure the energy of a system, and that is given by the expectation value of the Hamiltonian of the system. That is, energy E is equal to the expectation value of the Hamiltonian of the system, and that is given by bra psi operator H ket psi divided by the normalization factor. If you want to use the complete set of eigenvectors ket psi n of any operator A as a basis, then in that case expectation value of operator A will be given by 1 by bra psi ket psi into summation nm bra psi ket psi m bra psi m operator A ket psi n bra psi m n into ket psi. So here we have used the basis of the eigenvectors that will be written as summation n a n modulus bra psi n ket psi square divided by bra psi ket psi. Here we see that the quantity gives the probability Pn of finding the value An after measuring the observable A. Therefore, we can interpret this as expectation value of operator A is equal to summation n a n p n. That is, the expectation value of an observable can be obtained by adding all the permissible eigenvalues an with each an multiplied by the corresponding probability. That is, this can be written as a1 into p1 plus a2 into p2 plus a3 into p3 plus that so on. That means if you want to find the expectation value of an operator A, then what you will have to do is get the summation of all the product of the eigenvalues with the multiplied with the corresponding probability of finding that eigenvalues in the corresponding eigenstate. And this is the case for the discrete spectra. If you want to extend this for a continuous distribution of probabilities PA, then it can be written as expectation value of A is equal to integration minus infinity to infinity A modulus A psi A square dA divided by normalizing condition modulus psi A square dA, and that is also again can be written as integration minus infinity to plus infinity A d p A. This is how we can calculate the expectation value of an operator for a given state vector ket psi or any wave function psi. Friends, the expectation value of an observable can be obtained physically by preparing a very large number of identical systems, each in the same state, say ket psi. Then the observable A is measured on all these identical systems. The results of these measurements suppose are A1, A2, A3, and A dash, AN, and so on, with the corresponding probabilities of occurrences are P1, P2, dash dash Pn, then the average value of all these repeated measurements is called the expectation value of the operator with respect to the state gate psi. That means this equation. Now we will solve some problem to make the concept of expectation value more clear. So let us do that exercise. Let us consider a system whose state is given in terms of a complete and orthonormal set of five vectors phi1, phi2, phi3, phi4, and phi5 as follow. That means the state is given in terms of the linear superposition of these five vectors, where phi n are the eigenstate to the system's Hamiltonian given by Hamiltonian kit phi n is equal to n epsilon naught times kit phi n, where n is an integer and epsilon naught is the energy for energy unit. Now, if the energy is measured on a large number of identical systems that are all initially in the same state, Kate psi, then find what values would be 1 of 10 and with what probabilities. Second problem, find the average energy of one such system. Let us solve this. Firstly, we will determine whether this state is normalized or not. If it is normalized, then there is no need of using the normalization constant again and again. If it is not normalized, then we will use the normalization constant, normalization factor, bra psi, ket psi in the calculation. So let us calculate this factor. So bra psi, ket psi can be calculated as this 1 by square root 19 ket phi 1 plus 2 by square root 19 ket phi 2 plus square root whole 2 by 19 ket phi 3 plus square root whole 3 by 19 ket phi 4 plus square root 5 by 19 ket phi 5 bracket star into 1 by square root 19 ket phi 1 plus 2 by square root 19 ket phi 2 plus square root 2 by 19 ket phi 3 plus square root 3 whole by 19 into ket phi 4 plus square root 5 by 19. Now, after simplification, we'll get 1 by 19 plus 4 by 19 plus 2 by 19 plus 3 by 19 plus 5 by 19 is equal to 15 by 19. And we have used here the properties of bra phi j ket phi k is equal to Kronecker delta jk. So for the bra phi 1 ket phi 1 the quantity will be 1, and for the phi 1 bra phi 1 ket phi 2 the quantity will be 0, and so on. So we have used this concept to calculate this, and we are getting the normalization constant is 15 by 19. That is, the state is not normalized. So we will use this normalization constant. So firstly, we will find the part A. Now we have to find the energy on a large number of identical systems that are all initially in the same state, Kate psi. To find the energy, we will have to get the expectation of the Hamiltonian of the system, where Hamiltonian operated on Kate phi n is given equal to n epsilon naught phi n. Therefore, the energy En can be calculated by the expectation of bra phi n Hamiltonian operator is Kate phi n. Bra phi n n epsilon naught Kate phi n, where n is equal to 1, 2, 3, 4, 5. Therefore, for each state, we will calculate the energy. So, for state phi 1, E1 is equal to phi 1 epsilon naught Kate phi 1, that is equal to epsilon naught. Similarly, we can calculate Et is equal to phi 2 2 epsilon naught. Phi 2 get phi 2 is equal to 2 epsilon naught, and E3 is equal to 3 epsilon naught, and E4 is equal to 4 epsilon naught. Similarly, E5 is equal to 5 epsilon naught. With and we will also calculate the corresponding probabilities of measurement of the state and getting it into the any of the five vectors. So corresponding probabilities for measuring energy E1, P1 is equal to given by modulus square phi 1 psi square divided by normalizing factor, and that will be equal to 1 by square root 19 bra phi 1 kate phi 1 whole square, that will be equal to 1 by 19 into 19 by 15 is equal to 1 by 15. Similarly, we can calculate for energy E2, probability is equal to P2 is equal to modulus square bra phi 2 kate psi square divided by bra psi kate psi, and that is equal to 2 by square root 19 into phi 2 into phi 2 square into 19 by 15, and that gives equal to 4 by 15. Similarly, we can have values P3 is equal to 2 by 15, P4 is equal to 3 by 15, and P5 E5 is equal to 5 by 15. Thus, we have the values of the energy corresponding to the each vectors with the corresponding probabilities of measurement we found in the respective eigenvectors. Friends, now we will calculate the average energy of one such system. So we can calculate this average energy by two methods. First is the average energy of a system can be given by E is equal to summation j is equal to 1 to 5 because there are 5 eigenvectors given. P j E j is equal to P1 E1 plus P2 E2 plus P3 E3 plus P4 E4 plus P5 E5, and that is equal to E1, E2, E3, E4, E5, are respectively epsilon naught, 2 epsilon naught, 3 epsilon naught, 4 epsilon naught, and 5 epsilon naught. And we have already calculated the probabilities of measurement of these energies. So we can substitute these values. So 1 by 15 into epsilon naught plus 8 by 15 into epsilon naught plus 6 by 15 into epsilon naught plus 12 by 15 into epsilon naught plus 25 by 15 into epsilon naught. That will be equal to 52 by 15 epsilon naught. So total energy of the system is equal to 52 divided by 15 epsilon naught. And this total energy we can calculate by directly using the formula E is equal to expectation value of Hamiltonian. So we'll directly use this formula to get the total energy, and that can be given by the normalizing constant for this state psi we calculated was 1 by 15 divided by 19 into Kate psi Hamiltonian H psi, sorry, bra psi Hamiltonian Kate psi, and this can be calculated as 19 by 15 into summation of n is equal to 1 to n is equal to 5 an square phi n h phi n, and that will be equal to 19 by 15 into this value will give total energy. This value will be given by 1 by 19 plus 8 by 19 plus 6 by 19 plus 12 by 19 plus 25 by 19 into epsilon naught. So we get total energy is equal to 52 by 15 epsilon naught. Here we have used Kate psi is equal to an Kate phi n is equal to 1 to 5, and then we get this. Friends, this is for now. In this video lecture, we just discussed about how the measurement in quantum mechanics disturbs the system and how we can calculate the expectation values of any operator with respect to given wave function psi. And we also learned that how to get the probabilities of the corresponding measurement in a given state Kate psi. Friends, I hope that you learned through this video lecture and enjoyed the video lecture. If you have not subscribed the Sai Academy channel till now, please subscribe it and share this video with your friends and colleagues so that they can also learn about these important concepts, because these concepts are very important and are used to ask in the many competitive examination like CSIR, like BARC, entrance examination for the scientific services, as well as the academics in master level courses. So, friends, remain stay tuned and press the bell icon so that you can get the notification of the upcoming videos because we used to provide you the video lecture on important topics of the physics so that you can get benefited by learning the physics through our Sci Academy channel. Thank you, friends.